Let's spend the last couple of minutes think a little bit about communication more abstractly. And this is where part of the most interesting sort of research is happening these days. So I spent the first part of the lecture pissing on buses, right? But they're very good because they're actually fairly inexpensive. And conceptually, if they're sort of reasonably short, or if you have the time to spend, I can communicate, anybody can communicate with anybody else, quote, in one step. It's a slow step, but if I have the time to have this sort of slow step, the time for information to get anywhere in the system, the bus is a very economical way to do it. The hardware cost is low. A variant on the bus, which uses nothing but point-to-point links, is a ring. Okay, and in fact, a lot of the early multi-core machines used a simple sort of ring to sort of collect information from all the processors and send it around, because it has the engineering advantage of being made up of think of this as a segmented bus, where each segment of the bus, there's somebody who takes the information from the previous segment and says, I'll just reclock that data, get rid of any noise, put it out, and it's only going to go from me to you. So it's all point to point. So rings are nice. They solve some of the electrical difficulties here. They still have it takes a little longer to get all the way around. But if it's really about sort of messaging from one, to neighbors, rings are very good. And in fact, all the neighbors can communicate with each other at the same time. Whereas here, only one communication can happen at once. So rings are a communication topology, which are very effective for a whole class of communications. Moving up a level, we can talk about costs that are sort of go now as the number of nodes, right? We can have here we have a complete graph, so all the nodes can choose to communicate to each other at any given time. The hardware is quite expensive because notice each node is pretty much prepared to transmit and receive to all of its neighbors all at the same time, not just a single neighbor. Okay, but you get very, very good communications. There's no complication here. If I want to communicate to you, I just dump data on the wire that connects us. So in some ways, we're making communications very high bandwidth at the cost of having to spend a lot of hardware on the wires and on the interfaces on those wires. A slightly more elegant approach, perhaps, is a crossbar switch. So imagine the A's were all your processors, and B's were all your memory modules. And this would be a way in which it would be possible for each processor to access a different memory module all simultaneously. So with carefully orchestrated communications, it would be possible for every CPU to talk to every memory system. And the less orchestrated thing is possible for you to get everywhere, okay, but you may get some collisions, right? And so this is one of these probabilistic things now, where depending on how you engineer the synchronization and communication protocols, you can sort of make a balance between getting very high throughput through a crossbar, or it basically, everybody trying to access B1, in which case the crossbar really turns out to be a bus, where we have to all line up and communicate one at a time. But in a large system, it's unlikely that everybody will want to get the same memory location at the same time, particularly when there's caches here buffering up most of the transactions. So crossbars are very popular in the so-called small SMP, symmetric multiprocessors that have 2 or 4 cores. They often have a crossbar switch to deal with things like that. Moving up one more time, now we've given up. We've basically said, look, there's too much collision happening here. I'm going to make communications happen like it happens in Manhattan. You get to travel on streets. There's point-to-point communication. There's this notion of I can route a message from here to here. Go east and then north and then east. And there's several paths, so there's possibility of avoiding hot spots in your communication network. The mesh can be regular, or it can be sort of incomplete. And so modern, high-speed networking, the internet that we're used to, is really some sort of mesh, right? Where some of the communication links have very high bandwidth. This is a very organized mesh, something like that you might put into an integrated circuit. The advantage of this mesh is that there's no wires that have to get all the way across the chip, right? So the wires can be very fast. Long wires are inherently slow. We avoid that with sort of this. And in fact, there's really nothing to prevent us from doing 3D interconnects of one sort or another. So these mesh topologies have been very popular as people start thinking about how to hook together, say, 100 or 1,000 processors. How should they communicate with each other? And typically they use meshes like this with the memories and the I/O system connected at the edges of the mesh, and the middle part of the mesh is completely full of processors communicating one to another. It's possible to build networks that have latencies that don't go as in this case, the square root of n, okay, some root of n, which is what these all do. But instead, we use a tree-like mechanism. These are pictures of hypercubes, or more generally a tree, in which case the longest path from one node to another is logarithmic. Okay, we have trouble embedding 4 cubes in 3 space, so these sorts of hypercubes work well up to a certain point, and then either we have to figure out how to invent more dimensions, or we move to a logarithmic mechanism like this. There was a whole interesting set of technologies called fat trees, which they used a tree-like architecture, and they made these links, which are obviously critical for communicating between this half and this half, have considerably more communication bandwidth than those links. So the idea is the trees got fatter as you got to the top, and the idea was to sort of balance out the advantages of the logarithmic latencies with the increased communication capacity you needed at higher levels. And depending on what you're trying to achieve, any of these topologies may in fact be best. So you as architects will have a lot of different choices to make. Okay. So we can go off and talk about the hardware cost, which is associated with the number of links that are active at any given time, and the theoretical latency, how long does it take to communicate a message from one processor to another. And so this is sort of the theorist view. And just because we occasionally dip into realism, if we take into account, first of all, that some wires are long, like in the fat tree. There was this notion that all the nodes didn't all fit into a tiny little space. As you put more and more nodes, some of them got farther apart, and some of the wires had to get longer. Okay, and plus the fact that light doesn't travel infinitely fast, we can sort of change this to reflect physical reality. In other words, some of these things where the asymptotic costs seem to be low, if we put in the fact that nodes have to be physically separate and things like that, we discover that these are the actual sort of lower bounds on the latencies that we get. So remember, you can have a theoretically nice thing, but when you package it up and sell it to the masses, you have to keep track. So where is all this going? Well, I think that, as I said earlier, communication at sort of between components on your system, that seems to be serial point-to-point links. Networking, that seems to be a strategy that we figured out, and we use very high-speed point-to-point links, increasingly high-speed. The real challenge now is when we have hundreds of communicating processors all on one chip, we start having some more interesting conversations about possible interconnects. So if you go off and become an architect at Intel or some other modern processor company, you'll probably revisit all these conversations, but now talking about things that are an inch across. So your scale is much smaller than worldwide, but many of the same problems are still there.